Hello everyone. Today we will begin a series of lectures on a new chapter which covers additional topics in trigonometry. We'll begin with the law of sines, which is a special law with a set of its own formulas which help us use trigonometry to solve for any triangle. We will be able to apply trigonometry and find angle measures and lengths of sides for any triangle. So far, we've only learnt using trigonometry on right triangles. With the law of sines and later on the law of cosines, we will be able to apply trigonometry to any triangle. The objectives of this lecture will be to use the law of sines to solve oblique triangles. Oblique triangles are those that are not right triangles. Then we learn how to use the law of sines to solve, if possible, the triangle or triangles in the ambiguous case. We will have to understand first what we mean by ambiguous cases and then find the area of an oblique triangle using the sine function, and finally we learn how to solve application problems using the law of sines. Let's begin by defining oblique triangles. An oblique triangle is a triangle that does not contain a right angle. In other words, they are triangles which are not right angle triangles. Now there can be two types of oblique triangles. One in which all three angles are acute angles. Acute angles are angles that are less than 90 degrees, angles that measure between greater than 0 degrees but less than 90 degrees. So an oblique triangle has either three acute angles or it can have one obtuse angle. An obtuse angle is one which is greater than 90 degrees but less than 180 degrees. So it can have one obtuse angle, and obviously the other two angles in that case would have to be acute angles. Now, one important thing to remember about oblique triangles and trigonometry is that the relationships among the sides and angles of right triangles do not apply to oblique triangles. In other words, the definition of the sine ratio of opposite over hypotenuse, and for the cosine, the adjacent over hypotenuse, the tangent opposite over adjacent, these ratios, these definitions do not apply to oblique triangles because there's no hypotenuse in an oblique triangle. Hypotenuse only applies to right angle triangle. All right, so you have to keep in mind that the relationships that we learnt in trigonometry as applied to right angle triangles do not apply to oblique triangles. Let's look at the law of sines and its related formula. It says here if A, B, and C are the measures of the angles of a triangle and the sides A, B, and C in lowercase are the lengths of the sides opposite these angles, then the side A over the sine of angle A will be equal to the side B over the sine of angle B will be equal to the side C over the sine of angle C. The ratio of the length of the side of any triangle to the sine of the angle opposite that side. So side A over the sine of the angle opposite side A would be angle A. That's how it would be marked. Similarly, side B divided by the sine of the angle opposite side B would be labeled as angle B, and same for C. And this applies to any triangle, not just right triangles, but any triangle. It includes all kinds of oblique triangles, whether it's one with three acute angles or one with an obtuse angle. The law of sines applies to any triangle. Let's talk about solving oblique triangles. But before that, what do we understand by solving for an oblique triangle? It means we will be finding the lengths of all three sides of the triangle as well as the measures of all three angles of any triangle. Of course, we'll be applying the law of sines. However, we have to be given some basic information about some of the sides and some of the angles. And there are two cases using which we can apply the law of sines and find the unknown sides and angles. One of them is a side and two angles, abbreviated as SAA. That means as long as we are given one side and any two angles, we will be able to use the law of sines and find the measures of the remaining sides and the angles. The other case is when we are given two angles and the length of the side in between the two angles. That's very important. They have to give us the measures of two angles, and the side measure that we need is the side that falls between the two angles. And the way they've written it out is ASA, where S, representing the side, is between two A's. That tells us that we need to know the length of the side between the two given angles. All right. So as long as these two cases are provided, any one of these two cases is provided, we should be able to apply the law of sines and solve for oblique triangles. All right. Let's work on an example of solving for a triangle given the measure of one side and two of the angles. We have to use the law of sines, but let's look at the problem. It says solve the triangle with angle A equals 64 degrees, angle C equals 82 degrees, and side C equals 14 centimeters, round lengths of sides to the nearest tenth. The first thing to do is to draw a triangle, label it correctly, and put in the values that have been provided to us. So here we have an oblique triangle. This is not a right triangle. Just make sure that you have labeled the sides correctly. The side opposite to a particular angle is labeled with the lowercase of the angle label. So angle A, marked with a capital A, has a side opposite marked as lowercase a. Similarly, angle C has its opposite side labeled as lowercase c, and then angle B has its opposite side labeled as B. Fill in the angle measures and the side measures that we know of. Angle A has a measure of 64 degrees, angle C has a measure of 82 degrees, and side C has a measure of 14 centimeters. Now, we've been asked to solve for the triangle, which means that we have to find the value of all sides and all the angles of this triangle. We are already given information on two of its angles and one side. However, we have to find the value of the remaining angle, which is angle B, and two unknown sides. Correct? So we'll start by finding the measure of angle B. And that we can do using simple geometry and algebra. The sum of the three angles of any triangle is 180 degrees. We have been given the angle measures of two of the angles. Therefore, you can just sum the two given angles and subtract the sum from 180 degrees to get the measure of angle B. So that's the first step. Angle A plus angle B plus angle C equals 180 degrees. Let's plug in the value of angle A and angle C. So we'll have 64 degrees plus B, which is the unknown angle we are trying to find. And C has a measure of 82 degrees, all equal 180 degrees. We can sum up 64 and 82 degrees for a value of 146 degrees plus B equals 180 degrees. We solve for B. 180 degrees minus 146 degrees equals 34 degrees. So that is what the measure of angle B is, 34 degrees. So now we know the measures of all three angles of the triangle. The next exercise will be to find the measure of side A and side B. Correct? Now, we cannot use the trigonometric ratios to find the unknown sides because this is not a right triangle. Trigonometric ratios that we've learned previously only apply to right triangles. This is an oblique triangle, and for that we have the law of sines that we must use. All right, so we will set up our equation using the law of sines. Now, first we will find the measure of side A. In order to find side A, we have to set up our equation such that it involves side A as well as sine of A. And we have side C as well as angle C known to us. Therefore, the equation that we'll set up is A divided by sine of A equals C divided by sine of C. Recall that the law of sines is A divided by sine of A equals B divided by sine of B equals C divided by sine of C. However, when we are working on finding the measure of one side, then just take the ratio which has both the side and the angle measure known, and then the unknown side and its corresponding angle, which must be known. All right, there can only be one unknown in this setup. In the next step, what has been done is they have cross multiplied. So A times sine C equals C times sine A, which gives us A equals C times sine A divided by sine C. So this is what they've done. They have A times sine C. They've divided both sides by sine C in order to isolate the lowercase a. So we have C times sine of C. So now we'll just plug in the values. C has a measure of 14. Angle A has a measure of 64 degrees. So in the numerator, we have 14 times sine of 64 degrees divided by sine of 82 degrees, which is the value of angle C. And once we use our calculators to evaluate this, we come up with a value of 12.7 centimeters for side A. All right, so this is how we will be finding side B, but there we will need B over sine B. All right, let's go on to the next slide to finish this off by finding side B. Let's complete this problem by finding the measure of side B. We already know the measures of all three angles. We know the measure of side C. We found the measure of side A. We now need to find side B, and that will complete this problem. So we have to now set up the equation with side B in it. The value of angle B is 34 degrees. We found that out. So the equation is B divided by sine of B equals C divided by sine of C. We could have also used A divided by sine of A to solve for B now that we have found the value of side A, but we'll just use C divided by sine of C. So again, cross multiply B times sine C equals C times sine B, and then solve for B, which is equal to C times sine of B divided by sine of C. Again, they have divided both sides by sine of C in the previous step to come up with the equation B equals C times sine B divided by sine C. We just plug in the values of the side and the angle measures and then use our calculators to evaluate this expression. We get 7.9 centimeters for side B, for the length of side B. All right. We will now work on an example which is on solving an ASA triangle using the law of sines. What do we mean by ASA? Let's look at the arrangement of the letters here. A stands for angle and S stands for side. And we see in this arrangement of the letters, S, which is the side, is between two A's. And that is exactly the information that will be provided to us in order to solve for the triangle. We will be provided information on two angles and the side in between the two angles, right? So the question says solve triangle ABC if A equals 40 degrees, C equals 22.5 degrees, and B equals 12. Now in this ASA model, B should be the side in between the two angles. So let's go through solving this problem here. But first, in the triangle figure given to us, let's mark angle A as 40 degrees and C is 22.5 degrees. This angle here is 22.5 degrees, and the side in between the two angles will be indicated by the letter B because it's the side that's opposite angle B. Correct? So it's going to be B equals 12 for the side that has been given to us. Let's mark the other sides of the triangle. The side opposite to angle A will be labeled with lowercase a, and the side opposite angle C will be labeled with a lowercase c. So for this problem, we will need to find the values of the sides A and C as well as the angle B. Those are the unknown quantities that we will need to solve for. Alright, now since we've been given the values of two sides of the triangle, we can find the third side by summing up the two given angles and subtracting the sum from angle B. So that's the first step. Again, A plus B plus C equals 180 degrees. Therefore, plug in the values of the known angles. 40 degrees for A, 22.5 degrees for C, and B is the unknown angle. Sum up 40 plus 22.5 gives us 62.5 degrees, plus B equals 180 degrees. So to solve for B, we subtract 62.5 degrees from 180 degrees for a value of 117.5 degrees. So we have the angle measure for angle B, that's 117.5 degrees. The next is to find the lengths of the side A and side C. This time we will have to set up our equation using the law of sines. Let's look at the way it's been set up. We want to find A first. So B divided by sine of B. Since the side B has been given to us and now we know the value of angle B, we also know the value of angle A. So in order to find the length of side A, we cross multiply like we did in the previous example. So B times sine of A equals A times sine of B. Therefore, A will be B times sine of A divided by sine of B. And now we can go ahead and plug in the values. So B has a value of 12. Angle A is 40 degrees. So 12 times sine of 40 degrees divided by B. Angle B has a measure of 117.5 degrees. So just make sure that you are plugging in the values correctly. So sine of B will give us 8.7 approximately as the value for A. Therefore, A will have a value of 8.7 units. We still have to solve for the unknown side, which is C. So again, set up your equation using the law of sines, but this time we must have a ratio using the side C and the angle C. Therefore, B divided by sine of B equals C divided by sine of C is the equation that we are going to use here. Again, cross multiply. B times sine of C equals C times sine of B. So here we go. C times sine of B equals B times sine of C. We're solving for C, therefore we are going to end up with B times sine of C divided by sine of B. Plug in the values correctly. Side B has a measure of 12, sine C would be sine of 22.5 degrees. That's the angle value for C. And then sine of B would be sine of 117.5 degrees. And once we complete this calculation using our calculators, we get a measure of 5.2 for the length of side C. Therefore, the three sides have measures A equals 8.7, C equals 5.2, B equals 12, and the angle measures are angle A 42 degrees, angle B 117.5 degrees, and angle C is 22.5 degrees. Right? So far, we learned about two cases of solving for a triangle using the law of sines. The first one was SAA, where we were given the measure of a side of a triangle and any two angles, and we had to find the measures of the unknown sides and the unknown angle. The second was the ASA, when we were given information on two angle measures of a triangle and the side in between those two angles. There's a third case known as the SSA, and it's also called the ambiguous case. We'll talk about why it's called the ambiguous case, but SSA means that we'll be provided with the length of any two sides of the triangle and an angle opposite one of the two sides. Right? And when this situation happens, it can lead to three situations. The first one is we can get just one triangle, or it could lead to two triangles or no triangle at all. We will go through the different situations that might arise from the ambiguous case when we are provided the measures of two sides and an angle opposite one of the two sides. So the third case that we are learning about is the SSA, when we are given information on two sides and an angle opposite to any one of those two sides. It's also known as the ambiguous case because it can lead to three possible situations. The first one could be a situation where we get only one triangle using those measures. The second one, when there could be no triangles possible. And the third one, where there could be two triangles possible. Let's just spend some time on each of these three cases. Now, as far as one triangle is concerned, there is a possibility of two different types of triangles. It's still one triangle, but it could be either an oblique triangle or it could lead to a right triangle depending on the dimensions of one of the sides. All right, so here in this picture, we see it's an oblique triangle. Now, we are given information on side A, side B, and the angle opposite side A, this angle A. So we are given information on two sides and an angle A, which is opposite to side A. So that satisfies the SSA condition. Now, an oblique triangle will happen if one of the sides, so let's take side A, if side A is greater than the height of the triangle, denoted by the letter H, and A is also greater than side B of the triangle. So when A is greater than the height of the triangle as well as the length of side B, then it's a situation where we get one triangle, which is an oblique triangle. The second case for one triangle is when side A has the same length as the height of the triangle. Now, the height of any triangle is always perpendicular to the base, correct? So when side A is the same as the height of the triangle, that will make it a right triangle. So in cases where only one triangle is possible, we could either have an oblique triangle if the side A is greater than the height and side A is greater than the length of side B. All right, so if these two conditions happen, then it's a one triangle which is an oblique triangle. For one right triangle, A is equal to H, it will result in a right angle triangle. The case which is no triangle is possible with the measures given. A is less than H and is not long enough to form a triangle. So if side A is less than the height of the triangle, then it will not reach the base of the triangle. Therefore, in that situation, no triangle is possible. And then the last case is where two triangles are possible, and that happens when A is greater than the height of the triangle and A is less than B. So in other words, for two triangles to occur, A would be greater than the height of the triangle and A would be less than the length of side B. In that case, we would have two distinct triangles that could be formed using the same dimensions provided to us in SSA. All right? Let's go through an example of an SSA case where we end up with no solutions. That means no triangle is possible. They've given us the measures of a triangle which has angle A equals 50 degrees, the side A equals 10 and side B equals 20. We have to solve for the triangle, which means find the measures of all the other unknown sides and other angles of the triangle. However, there are three situations possible. Either we could end up with one triangle, and within one triangle we could either have an oblique triangle or a right triangle. The second case would be where no triangle is possible, and the third case is where two triangles are possible. Now they've already told us that in this case will result in no solutions. That means no triangle will be possible. However, if you recall, they said the case of no triangle happens when the side A is less than the height of the triangle. So we could, right at the start, do a comparison of the side A with side H. Now, how do we do that? They haven't given us the measure of the height of the triangle. The formula using trigonometry to find side H is H equals B times sine of A. All right, so B we know is 20, correct? So let's write it here. H equals B times sine of A. So H equals B is 20 and sine of A would be sine of 50 degrees because A has an angle measure of 50 degrees. And once you do the calculation for 20 multiplied by sine of 50, we approximately come up with a measure of 15 units. All right, 15.3 units. So now let's go back and compare 15 with A, which is 10, correct? So A is A less than H. A has a measure of 10. H has a measure of 15. A is less than H. We can immediately conclude that this is a case of no solutions. There's no point moving further to find the sides or solving for the triangle because it is not a triangle at all. Right? But they've done it a little bit differently. Let's go through the steps here. They've used the law of sines and they have set it up as A divided by sine of A equals B divided by sine of B. In the next step, they will be plugging in the values. Side A has a value of 10. Sine of A is sine of 50. Then we have 20 for B and sine of B is unknown. So they'll try to solve for sine of B first. Cross multiplying, we get 10 times sine of B equals 20 times sine of 50 degrees, and then we solve for sine of B, which is 20 times sine of 50 degrees divided by 10, which gives us sine B approximately 1.53. We cannot find an angle whose sine ratio is 1.53. There's no way we can find an angle whose sine ratio is 1.53 because if you recall, ratios for a sine function extends from -1 to +1. We cannot get a ratio which is more than 1. So we have 1.53. So that's another way of knowing that there's no angle B for which the sine is greater than 1. Therefore, no triangle is possible with the given measurements. So you could solve it either way, either by first finding the height of the triangle using the formula B times sine of A and then comparing it with the length of side A, and we can come to the conclusion that a triangle is not possible because A is less than the height of the triangle, or you can solve it using the law of sines until you get to a point where you get the sine value which is greater than the maximum point, the maximum ratio of the sine. There's no angle B for which sine is greater than 1. Therefore, the conclusion is that we cannot solve it. This is not a triangle. All right, so the case is, as given in this picture, no triangle possible. The next example that we will go through is solving an SSA triangle using the law of sines, which will result in two distinct triangles. Two solutions. Solve triangle ABC if A equals 35 degrees, side A equals 12 and side B equals 16. So let's go through the steps here. We could outright first check if any triangle is at all possible by comparing the length of side A with the height of the triangle. Again, how would you know the height of the triangle? By using this formula, height equals B times sine of A. And if the side A is less than the height of the triangle, then we can conclude that no triangle is possible. However, they have told us that for this example, two solutions would be possible. Two triangles would be possible. So let's go through the steps here. First is to set up the problem with the law of sines. A divided by sine of A equals B divided by sine of B. So we'll plug in the values. A has a measure of 12. Angle A has a measure of 35 degrees. So 12 divided by sine 35 degrees equals B has a measure of 16, the side B, and angle B is unknown, so that remains as sine B. So we will solve for the angle B here. So 12 multiplied by sine B equals 16 multiplied by sine 35 degrees is what we'll get after we cross multiply, and then we divide both sides by 12 to isolate sine of B, and we end up with sine B equals 16 times sine 35 degrees divided by 12. When we calculate the right hand side, we end up with sine of B approximately 0.7648. Now this ratio is within the range -1 and +1. Like previously, we got a ratio which was greater than 1, 1.53, and we concluded that no triangle is possible because sine ratio does not extend beyond a ratio of 1. Here we have the ratio as 0.7648, so we can proceed. We have to find the angle whose sine ratio is 0.765 approximately, and that would be the measure of angle B. So we write it as inverse sine or arc sine of 0.7648 is equal to 50 degrees. Correct? Now, we can have two angles between 0 and 180 degrees for which sine of B is equal to 0.7648. Recall that sine can be a positive value. In the first quadrant, it can be a first quadrant angle with a positive ratio, as well as a second quadrant angle with a positive ratio. So even though we found 50 degrees for the measure of angle B, that's a first quadrant angle, but we can also have an angle in the second quadrant. So that is what tells us that we will end up with two solutions, two distinct triangles. All right. Now that we have found the measure of the first quadrant angle for angle B, whose sine ratio was 0.7648, the angle measure was 50 degrees. So we know one of the measures of angle B. However, we said that the angle could either be in the first quadrant or in the second quadrant, correct? So if the measure of angle B is equal to 50, then just add up the two angle measures. 35 degrees plus 50 degrees equals 85 degrees. Now to find B sub 2, which is the second quadrant angle, if you subtract 50 degrees from 180 degrees, the way you find reference angles, you will come up with 130 degrees. So we are essentially using the formula for reference angles, but here we are finding the second quadrant angle. All right. So the second quadrant angle will be 130 degrees, whose reference angle is 50 degrees, so to speak. So if we add up the measure of angle A with the second measure for angle B, denoted as B sub 2, it's equal to 35 degrees plus 130 degrees, which is equal to 165 degrees. So A plus B1 is less than 180 degrees in one case, and A plus B sub 2 is less than 180 degrees. So because both these sums are less than 180 degrees, that tells us there are two possible solutions, and we can go ahead and complete solving for the rest of the triangle. And that's what we will do in the subsequent slides. Now that we have determined there'll be two triangles, we have to solve for both the triangles. One which has angle B as a measure of 50 degrees, the other one has an angle of 130 degrees. So we know that in both cases, angle A will be equal to 35 degrees. So let's write that. A equals 35 degrees in both cases. We have to find the measure of angle C, which is A plus B sub 1 plus C sub 1 equals 180 degrees. Plug in the values that we know, which is 35 degrees plus 50 degrees plus C sub 1 equals 180 degrees. Therefore, C sub 1 will be equal to 95 degrees. When you subtract 85 from 180 degrees, you get 95 degrees. Therefore, the angle measures are A equals 35, B equals 50, and C equals 95 degrees. For the second case, we have B sub 2 measuring 130 degrees, A equals 35 degrees. Again, we'll use the property that the three angles add up to 180 degrees, which will give us C being a value of 15 degrees. So 35 plus 130 plus whatever C2 is equals 180. 35 plus 130 is 165 plus C2 is 180. When you subtract 165 from 180, you get C2 equals 15 degrees. So for the second triangle, C has a measure of 15 degrees, A has a measure of 35 degrees, and B has a measure of 130 degrees. Now we'll find the remaining side. We know the measure of side A, we know the measure of side B. We need to find the measure of side C. Again, set up the equation using the law of sines, but this time there should be a C in the equation. So B divided by sine of B sub 1 equals C sub 1 divided by sine of C sub 1. Plug in the values. Side B has a measure of 16. Angle B sub 1 is 50. Therefore, 16 divided by sine of 50 equals side C divided by sine of 95 degrees. Again, cross multiply to solve for C. We get 16 times sine of 95 degrees divided by sine of 50 degrees gives us a measurement of side C, which is 20.8 units. As far as the second case is concerned, this time B sub 2 has a value of 130 degrees and C has a value of 15 degrees, correct? That's what we found. So set up the equation this time with B divided by sine of B sub 2 equals C sub 2 divided by sine of C sub 2. Plug in the values, but this time the angle used for B will be 130 degrees and for angle C it will be 15 degrees, correct? And again we solve it the same way. By cross multiplying, we end up with 16 times sine 15 degrees divided by sine of 130 degrees gives us a measure of side C as 5.4 units. Let's just summarize and put everything together so it's easier to understand which triangle has what measures. There are two triangles in one triangle. The solution is B sub 1 equals 50 degrees, C sub 1 equals 95 degrees, and the side C sub 1 is about 20.8 units, and we know the measures of the other two sides, which is A equals 12 and B equals 16, and angle A was given to us as 35 degrees. As far as the second triangle is concerned, it's the same measure for angle A, side A and side B, but for angle B, it's 130 degrees for the second triangle. For angle C, it's 15 degrees, and the side C in the second triangle is 5.4 units. We will now talk about finding the area of an oblique triangle using the rules of trigonometry. Now we all know that the area of a triangle is defined by the formula 1/2 multiplied by the base of the triangle multiplied by the height of the triangle. Now in this picture here below, we see that in the triangle ABC, AB is being considered as the base of the triangle, and the height is the perpendicular line running from the base all the way to the vertex of the angle opposite to the base, correct? So if we were to plug in the values in the formula using the variables given in this diagram, then we would write it as A equals 1/2. The base is denoted by the letter C, the small letter C, because it is located opposite to angle C, correct? So let's write C for the base and the height is H. So we can rewrite A equals 1/2 BH as A equals 1/2 C times H. Now using trigonometry, the height can be written as B times sine of A. Why so? Let me explain. We see here this H creates a right angle triangle. Again, the height will always run perpendicular, that is, always run at 90-degree angle from the base to the opposite side. So consider this side, this right angle triangle formed by drawing the height of the triangle. Therefore, if we know angle A and we are also given angle B, then the height is the opposite side over the hypotenuse, correct? B would represent the hypotenuse of this right triangle. So we can find H using the trigonometric ratio H equals B times sine of A, using the ratio that sine of angle A is equal to opposite over hypotenuse, H over B. And then if we solve for the height H, then we'll come up with B times sine of A. Therefore, in this formula, A equals 1/2 C times H. We can replace H with B times sine of A. And that is exactly what they've done when they came up with this formula 1/2 times B times C sine A. So C being the base, all right, they just switched the position of B and C, correct? It's 1/2 times C, which is the base, times B times sine of A is the formula for H using trigonometry. Now, depending on the side which you consider to be the base, the formula can change, correct? So let's say we consider side B to be the base, AC, or the side denoted by this lowercase b to be the base. In that case, the height would be a line running perpendicular from the base. So this is our base. We draw the height, which is the line running perpendicular from the base to the angle opposite to it. Right? So in this case, our right triangle is here. This is our right triangle. The base is denoted by B. So over here in this formula, you see we have B in the formula, and the angle C and the side A will be used to find H. This is our H. Therefore, the height would be A times sine of C. In that case, we are using this angle here. We are using this angle and the side A and the sine function to come up with H. And the formula, if B is considered to be the base, or the side AC is considered to be the base, is half times A times B times sine C. If we consider the side A to be the base, that is the line CB or BC, then the formula would be half times A times C sine B. So they should all give you the same value depending on which side you consider to be the base of the triangle. All right, that's why you see there's 3 different formulas given to find the area of an oblique triangle. We will now work on an example to find the area of an oblique triangle. The question says, find the area of a triangle having 2 sides of length 8 meters and 12 meters and an included angle of 135 degrees. We have the diagram given to us here. Let's mark or label the sides of the triangle. The side opposite angle C will be denoted by the small letter C. The side opposite angle B will be denoted by the small letter B, and that has a measure of 8 meters, and the side opposite angle A will be denoted as the side A, which is 12 meters. All right. Now the formula to calculate the area in geometry is, of course, 1/2 times base times height. Now we cannot use the side C to be the base because we don't know the length of side C. It's not given to us. We have to use one of the known sides as the base in order to find the area. We can either use the side B as the base or the side A as the base, but I'm going to use the side A as the base. All right. So let's draw the height of the triangle from side A, from the base all the way up to the vertex of the opposite angle, which is angle A. So I'm going to just drop a line which runs perpendicular to the base. So let's just assume that this is the height of the triangle running from the side labeled as A all the way up to the vertex of angle A. So in the formula given here, A equals 1/2 times B times H. B will have the value of 12. All right, that's the base. That's what we've considered to be the base. We have to find the length of the height of this triangle, and for that we will use a trigonometric equation. So we are going to use the sine function. So sine of the angle C, we have to use angle C because that is the only angle that is known. So sine of angle C will be equal to, sine is opposite over hypotenuse. The side opposite to angle C is H, and the hypotenuse is 8, which is B, correct? So we can write it as H divided by B, and then we solve for H, which gives us B times sine C, correct? So now we have an equation to replace H with, a trigonometric equation which we will use to find h. So in the next step, we rewrite this formula for the area as area equals 1/2. A represents our base, which will get replaced by 12, and then b times sine of c is what we came up with for h. So they've replaced h with b times sine of c. In the next step, we will plug in the values. 1/2 times 12, which is a. B is 8. So a is 12, b is 8, and c is 135 degrees. We have to do the computation. You can use your calculators for that, and we will come up with a measure of approximately 34 square meters, because the question said round to the nearest square meter. So that is how you can find the area of an oblique triangle using the rules of trigonometry. We will now work on an example, which is an application of law of sines in a word problem. The question says two fire lookout stations are 13 miles apart, with station B directly east of station A. Both stations spot a fire. The bearing of the fire from station A is north 35 degrees east, and the bearing of the fire from station B is north 49 degrees west. How far to the nearest tenth of a mile is the fire from station B? So essentially, the problem is about a fire which has been detected by two stations located at different points, and we have to determine how far the fire is from one of the stations, which is named station B. So let's try to draw a figure. Now they have drawn the figure here, but you will have to draw it yourself when you work on assignments and tests. So while this diagram is there, let's try to understand how they came up with this diagram. All right. Now, the first thing is two fire lookout stations are 13 miles apart, with station B directly east of station A. So we have to position the stations correctly relative to each other. So we'll start by marking a point for station A, and station B is directly east of station A and is at a distance of 13 miles from station A. Now, directly east means, let me just draw the north, south, east, west lines. The north, south, east, west lines intersect each other at right angles. We have north on top and then south at the bottom of the vertical line. Then to the right is east of the horizontal line. To the right of the horizontal line is east, and west is to the left of the horizontal line. Now, given this diagram, let's see where B would be located. It says it's directly east of station A, so that means it'll be directly 180 degrees to the right of station A. That's where B will be located, and the distance between A and B is 13 miles. So here we drew a line from A to B to begin with, and we marked the distance as 13 miles, right? And now we have to figure out where the fire is from each of these two stations, right? So C is where the fire is, and it says here the bearing of the fire from station A. So let's focus on station A. The bearing is north 35 degrees east. Therefore, we will draw a north-south line. This dashed line here is the north-south line. From station A, the bearing is north 35 degrees east. So from this point, from this north line, you have to turn right towards the east, because to get to the east from north, you have to turn right at an angle, at a certain angle. And what is that angle? That's the 35-degree angle. So here we have 35 degrees north and then east. And the angle is formed by moving in the clockwise direction, moving right of the north-south line. So that's 35 degrees. The next bearing is from B. The bearing of the fire from station B is north 49 degrees west. So again, we have the north-south line passing through point B. But this time we have to go west from this north-south line. So to go from the north to the west, we have to make a turn to the left, correct? So here is our north-south line, and we make an angle of 49 degrees in the anti-clockwise direction towards the left, and that is 49 degrees. So we have shown the bearings and we've shown the distance given to us in this map. We connect the points from A to C and from B to C to get an oblique triangle. However, so far all we can see is the length of the side AB given to us. We do not know the value of any of the internal angles within the triangle. But to find angle A, we can subtract 35 from 90 degrees because the north-south line makes an angle of 90 degrees with the ground, correct, with AB. So this north-south dashed line makes an angle of 90 degrees with the side AB, and we have this much of the angle as 35 degrees, correct? Therefore, we can find the internal angle of the triangle by subtracting 35 from 90 degrees. The same can be done to find the internal angle B. We can subtract 49 degrees from 90 degrees because the north-south line runs perpendicular to the line AB. Therefore, 49 degrees subtracted from 90 degrees will give us the internal angle of B. And that's what we do next. To find angle A, 90 degrees minus 35 degrees equals 55 degrees. So here angle A is 55 degrees. Let's mark that. And similarly, angle B will be 90 degrees minus 49 degrees, which is 41 degrees. Therefore, this angle here is 41 degrees. Now we can find angle C by summing up the two known angles A and B and subtracting that from 180 degrees. That will give us angle C. So the next few steps are just to find angle C. A plus B plus C equals 180 degrees. 55 is the value of A, 41 was the value of B, plus C is 180 degrees. We sum up 55 and 41 and get 96 degrees, plus C equals 180 degrees. Therefore, angle C has a measure of 84 degrees, correct? Therefore, 180 degrees minus 96 degrees gives us 84 degrees. So at this point, we have found all the angle measures of the triangle. We know one side. The next step will be to use the law of sines to set up an equation such that we can find the length of the side BC. That's what they have asked us for. How far is the fire from the station? Since the fire is at point C, we have to find the distance between B and C. We'll do that in the next slide. Let's finish off the problem now. We will need to find the length of BC. We already found the three angles of the triangle. Let's write that down. We had for angle A, it was 55 degrees. For angle B, it was 41 degrees, and angle C we found by adding up 55 and 41 and subtracting from 180 degrees, and that was 84 degrees for the value of C. We know the length of the side AB is 13 miles, so we have to set up an equation using the law of sines, which will have the side C in it. So I'm going to name this side AB as C, which is 13 miles. It's labeled C because it's the side opposite to angle C. Likewise, the side opposite to angle A should be labeled as lowercase a, and that's the side BC, and that's the side that we need to find the distance from B to C, how far the fire is from station B. All right, so let's get started here. We set up our equation using the law of sines. Side C divided by sine of the angle C is equal to side A divided by the sine of the angle A. We will now plug in the values for the different variables. Side C is equal to 13 divided by sine of angle C would be sine of 84 degrees equals, side A is unknown is what we need to find, but sine of angle A is sine of 55 degrees. And now we'll cross multiply to solve for A. To solve for A, it's 13 divided by sine of 84 degrees multiplied by sine of 55 degrees. In other words, 13 times sine 55 degrees divided by 84 degrees. It's the same thing. And when we complete the calculation, we come up with a distance of 10.707. So this side A has a measure of 10.707 miles. So let's write out the final answer. The fire is approximately 10.7 miles from station B. All right, we had to round it up to the nearest tenth of a mile, so we do not need to write the other two decimals. 10.7 miles is the distance from station B. Good enough of an answer. All right.